Good afternoon, everyone. It's fantastic that we all gather here today. I'm thrilled to face in front of our incredible customers, our valued partners, and esteemed partners. In the next 30 minutes, let's delve into the world of 5G non-terrestrial networks together. The fusion of space and mobile communications opened the door to unprecedented opportunities. Thank you for joining me today. We are entering a new space era. It has been more than 50 years since we have the first man walking on the moon. And after those golden years, there's a long time that there are a little less investment and interest in space technologies and satellite communications. The reason being that the situation is we have very expensive rockets, we have very expensive satellites, we have very long deployment time, and it's very costly, so only a few rich governments and countries can play the game. But the situation is very different now. There has been a hype recently in the space industry. As you can see, the investment in space blast off for the past few years. In 2020 alone, the investment reached like 7.6 billion US dollars. So now we are entering into a new space period. One of the biggest drivers is the miniaturization of satellites. As you can see, this is a CubeSat here. It's like 10 centimeter times 10 centimeter times 10 centimeter, and it's very lightweighted, only a few kilograms. So we are able to make the satellite smaller and still fully functional. And the cost is much lower because we made this kind of satellite out of off-the-shelf components. Yeah. And the launching fee is also a lot lower. For a satellite like this small, this one can become a second payload and to even decrease the cost of launching. Another driving force is space privatization. With all the big money pumping into the space industry, there are more and more new startups that are more creative, they are more efficient, and together they have changed the game rules completely. We all know that SpaceX has been wildly successful, so it forged the path for other companies to keep going. Yeah. And because of all these factors, we have cheaper rockets, we have cheaper satellites, we have more like internet technology, IoT technology. So it opened the door to like many novel new services, using the space data. But there's one problem exists. Even though that we have reduced the cost significantly in all the aspects about space industry, but for example, like starting to build up a complete constellation, that is still a lot of money, right? So for all the existing, for many existing players and the newcomers, an open standard is very important, because right now most satellite communication today is based on proprietary solution. For example, like Starlink has its own solution. No one can interoperate with its solution. So Starlink has to invest a lot of money, from the ICs, from the satellite, from the base station, and even to the user terminal. This all Starlink is like a closed system. But we know if you have an open standard, you can have different companies join the game to reduce the cost, to average out the investment and average out the risk. So many established and emerging participants favor the adoption of an open global standard. That is the situation that we are seeing right now. And in 2018, 3GPP is an industry collaboration organization, that is responsible for setting up many communication standards, including 2G, 3G, 4G, and 5G, and its evolution. So 3GPP jumped on the bandwagon of new space. So in 3GPP, it defines the so-called non-terrestrial networks, or NTN, for the integration of satellite and terrestrial networks. And they define the spaceborne and airborne vehicles as the carriers for the mobile signals. The spaceborne vehicles include GEO, MEO, or LEO, geostationary Earth orbit, and medium Earth orbit, and low Earth orbit satellites. Airborne vehicles include like HAPS, high amplitude platform systems, or UAS, the unmanned aerial system. And in 3GPP NTN, there are two types of communication standards. The NR-NTN is for broadband, and the IoT-NTN is for narrowband IoT applications. So what 3GPP already has for 5G is NB-IoT for narrowband communication, IoT communication, and 5G NR for broadband 5G communication. So the easiest way and the fastest way is to modify the existing working standards and add the space elements and make it become a non-terrestrial standards. So we can see the IoT NTN actually evolved from NB-IoT, and NR-NTN evolved from the 5G NR we are using on the ground right now. Yeah. But if you look at the throughput, it's still low compared to what we have in the terrestrial network. For NR-NTN, the throughput ranges only from 1 to 10 megabit per second. For IoT-NTN, is even lower. It's from 1 to 100K bit per second. And currently, because this is the very beginning of 3GPP non-terrestrial network, they only leverage satellites in the transparent bandpipe mode, which will be explained later. Okay, this is a visionary plot of the 3D network. As you can see, this is a multi-layer. You will see the labs, the HAPS, the LEO, and the GEO. It's multi-layers and multi-dimension. It's not only 2D, right? It's 3G. And you can see it will cover from the rural area, the urban area, and the remote area. So it's the 3D, the vehicle on the ground, airplanes in the air, and even satellites, they are all connected together. And this is a very complicated, global and ubiquitous connectivity. It's very dynamic. To reach this kind of complexity, to operate this kind of communication systems, will highly rely on AI and machine learning. And this is what we expect for 6G communications. There are still many challenges in front of us, and a lot of work to do, but we are definitely on the road. to explain the relationship, between like 5G beyond, and 6G, I think this figure explains it all. Before 5G, we have non-terrestrial networks, which is like SATCOM, satellite communication, and we have terrestrial network. These two things belong to two different worlds. Of course, they interwork with each other, but they only optimize their own system independently. So they only interwork, but they are not integrating together. And in 5G and 5G beyond, we are doing integration of these two systems, under a condition that the NTN development has minimum impact to current TN, terrestrial network. So the focus is still on terrestrial network, but we are adding the non-terrestrial features and functions for 5G and 5G beyond. But when we go forward in 6G, we will see the unification of the NTN and the TN networks. So we'll execute joint TN and NTN optimization. And the evolution path will focus on services, architectures, and technologies. Here I show the orbits and the spectrum of three major different satellites. The LEO. LEO, I think, is a very hot topic thanks to Starlink. The LEO satellite has an altitude around like 300 to 1,500 kilometers. And the satellite lifespan is pretty short. For example, Starlink LEO satellite has a lifespan usually less than 5 years. Since the LEO is closer to Earth, so it has the least propagation delay, which is very suitable for a lot of broadband communication. But the problem is you need a lot of satellites. You need a significant number of satellites, usually more than 40, to cover a certain area. In contrast, the GEO satellite is very far from Earth, right? The satellite height is around 35,000 kilometers. But you only need 3 satellites to cover the whole Earth. And usually the satellite life is very long. But the propagation delay is also very long. As you can see, they are moving at very different speeds. The LEO satellite moves really fast. It's around like 7 to 8 kilometers per second. And usually it will take, for example, less than 5 seconds to cross Germany. And the GEO satellite is not moving at all, right? So the speed is like, just like the Earth. And for satellite communication, they have a different definition in spectrum, in bands, compared to 3GPP. So usually we have L band and S band at the low frequency, and we have this KU, K, and Ka band as a high frequency range for satellite communications. 5G NTN has many use cases, and we can classify them by standards. For example, for IoT NTN, as I already mentioned, it's an extension of existing IoT on the ground. So, for example, if you get lost in mountains, right, you can use IoT NTN to send SOS emergency messages to get help. And for agriculture and farming in some remote area where there's no cellular service available, I think IoT NTN is perfect for the communication. And also you can use IoT NTN for global asset tracking or for disaster response and recovery. You can also use IoT NTN for remote monitoring, for example, the wind turbine on the sea. And of course, you can also use that for maritime and airtime applications. IoT NTN that's defined in 3GPP does not have the control mechanism of quality of service. So it's a best efforts approach for communication. In contrast, NR-NTN evolves from 5G NR. So it provides a broadband service. And with that broadband service, basically it's a ubiquitous continuity of 5G basic service, but extend to more areas. And we can use the NR-NTN for 5G fixed wireless access. And we can also use this as a 5G network backhaul support. So in the future, you will have like a base station on the ground, but the link between the base station to the core network or to the backbone data network will go through the NR-NTN satellite link. And you can also use NR-NTN for public safety operations and disaster response and recovery, and also like more advanced maritime and airtime connectivity. So through the NTN, you can have global ubiquitous connectivity no matter where you are, no matter you are in the rural area, a remote area, isolated area, or in the urban area. Let me introduce two different types of 5G NTN architectures. As you can see on the left, it's so-called transparent mode, or the transparent payload. In this configuration, we have the 5G base station, which is called GNOB or GMB on the ground. The core network, the 5GC or the next GC is also on the ground. So the satellite itself acts like a transponder. The satellite is only responsible for relaying the signal between the base station and the terminal device. In 3GPP, we call it user equipment, or UE. In satellite terminology, we call it user terminal, UT. So this transparent mode is defined in 3GPP release 17 and 18. Yeah. The pros of the transparent mode is the architecture is simple, right? The satellite, it's just like traditional satellite. It's do all the related stuff. But the cons is it's vulnerable to jamming attacks and amplifier noise. On the right-hand side, is a different mode called regenerative mode or regenerative payload. In this configuration, the base station is on the satellite. The core network is still on the ground. So you will have a gateway on the ground that talks to the base station on the satellite through the so-called feeder link. And the link between satellite to UE is called service link. So basically, you will have the base station on the satellite rotating the Earth. Yeah. And for example, like in the LEO satellite case, the satellite or the base station is not always directly connected to the gateway. So the signal has to do multi-hops through other satellites in the constellation through the inter-satellite link. So this is a very complicated scenario. And the process, the delay is shorter, right? Because the delay between the base station and the UE is only the service link. But the count is the satellite hardware and computing are much more complex. Let's talk about the challenges we are facing technically. The challenges of 5G NTN come from three main areas. One is the very long distance, from UE to satellite and back to the GNOB on the ground. And the second is the very large cell. The spot beams, can be as large as like 1,000 kilometers diameter. The third factor is the fast movement. The LEO satellite, at the altitude of 600 kilometers, can travel as fast as 7.5 kilometers per second. So all of these factors going to result in, for example, the long propagation delay, the poor link budget because of the very long distance, and high path attenuation. The fast movement will cause the Doppler shift, and the large cell beam will result in a significant differential time delay. And the fast moving of satellites will also cause frequent handovers. Because in this case, you are not moving, but your base station are moving. So you have to do handover very frequently. And we have to think of many new technical solutions to resolve these challenges. For example, we have to increase the number of repetitions, the HRQ process. We have to do tracking area update more efficiently. We have to invent a more clever conditional handover mechanism. So there's a lot. But I think 3GPP is working very hard on this. And also the spectrum is another challenge. Right now in release 17, we are using the low frequency band, the N256, the S band, and N255, the L band. But in release 18, which is supposed to be frozen this year, we will be using the higher frequency band, the KU band, KA band. The advantages of low frequency band is the path attenuation is lower. And this band has been used in legacy communication. So the components are available. But the challenge is the spectrum is very crowded, and you can easily get interference. And also the bandwidth is smaller. In contrast, for FR2 band with a high frequency band, you have bigger bandwidth, but this is like the millimeter wave in terrestrial network. But we have to use FDD, so you will cause potential interference. And also you need very high gain antenna front end. So the front end design will be more complex. This is a description of like a standard LEO communication. The satellite is moving, and the satellite transmits signal to the gateway through the inter-satellite link. For each satellite, because you want to cover as big area as possible, so you will form several so-called spot beams utilizing frequency reuse. And since the satellites are moving, right, so a UE or UT device on the ground will go through different kind of handovers. For example, if you travel from one spot beam to another spot beam generated by the same satellite, it's called intra-satellite handover. And if I travel from a spot beam to another spot beam by another satellite, so it's called inter-satellite handover. And it's also possible for you to move from one spot bin by the LEO satellite to another spot bin by a geo satellite. Yeah. So there are many different handover schemes and very frequently. So you can see this is a very complicated technical problem to resolve. And from the product verification point of view, we have to honestly mimic the satellite channel conditions so that to test our algorithm from the R&D phase and all the way to the production phase. The satellite channel can be divided into two parts. The one on the right is the traditional terrestrial model, and on the left is the new satellite link model. In the new satellite link model, we have three major elements here. One is dynamic delay. Since the satellite is moving, so the distance between the UE to the base station keeps changing. The angle keeps changing. So you need to have an accurate dynamic delay model. And also, since it's moving very fast, it will introduce a pretty high Doppler shift and also other dynamic attenuation like scintillation, rain, and cloud. Yeah. So to have a good tester, we need to cover all this channel model. So ALifecom, we implemented the NB-IoT features on our NE6000 network emulator. And we have a built-in channel emulator to mimic the real satellite channel. So you don't need an external channel emulator, which is very expensive. Yeah. This is our NE6000 GUI. We have a live demo station over there, and please spare time to take a look at the real demo during the break. And as you can see here, once the UT, we use a Quectel evaluation board, which has a MediaTek 6825 chipset on the board. We use that as our DUT. When the DUT or the UE is connected to our NE6000, an image of the phone will pop up. And you can see here, the satellite type is GEO. And we can enter the ephemeris info, which will tell the UE the coordinates of the satellite. And you can see the duplex mode is FDD in the red box, label number 3. And inside the red box, label 4, it will show you the timing relationship between the gateway and the UT. So the overall round trip time, RTT, is around 510 milliseconds. And we'll also show you the UE position and the gateway position. It's no doubt that ALifecom is a tester company, but we are more than a tester company. No. With developing core technologies for more than 10 years, we have a rich portfolio of 4G and 5G base station IPs. We can help our satellite customers to design the base station, the core network, and we can help them define their system. We can provide the physical layer IP. We can do the hardware architecture design. We can help them determine the spec and components. We can help our customers to do fast prototyping and help them to do all kinds of system integration. This is all I have for today. Thank you very much.